Welcome to Sleepy Science Hub. Tonight, we're going to embark on a peaceful journey to the most serene places in the universe. The cosmic cemeteries where stars rest after their long lives, and where some of these celestial beings find ways to gently awaken once more. As you settle into your comfortable space, let me know where in the world and at what time you're listening. Whether you're watching the stars appear in your evening sky or feeling the deep quiet of midnight settle around you, you're in exactly the right place for this gentle cosmic story. Tonight's tale might sound mysterious when we speak of zombie stars and undead suns, but I invite you to discover something far more beautiful than any earthly notion of the undead. These are stories of renewal and resurrection, of cosmic partnerships that breathe new life into stars that have completed their natural cycles. We'll explore how the universe has its own gentle ways of recycling stellar material, giving dormant stars the opportunity to shine once more through the most patient and beautiful processes imaginable. Take a moment to adjust your pillows, dim those lights, and let your breathing find its natural, peaceful rhythm. We're going to drift through the vast cosmic spaces where time moves differently, where stellar lifespans stretch across billions of years, and where death is not an ending, but simply a transition to a different kind of existence. These zombie stars represent some of the universe's most elegant solutions to the challenge of cosmic recycling, showing us that even in the depths of space, there are always opportunities for renewal and rebirth. These stellar resurrections happen not through any frightening or violent means, but through the gentlest possible cosmic processes: the patient accumulation of material, the slow rekindling of nuclear fires, and the beautiful dance of celestial bodies that have learned to share their essence across the vast emptiness of space. Tonight, we'll discover how death and rebirth in the cosmos are part of the same continuous cycle of stellar evolution. So get comfortable, take a slow breath, and let's begin our gentle exploration of the cosmic cemeteries where stars find their peaceful rest and sometimes their beautiful second chances at life. In the soft comfort of your evening sanctuary, imagine drifting through the vast expanses of space until you arrive at one of the universe's most peaceful and contemplative places, a cosmic cemetery where the remnants of ancient stars rest in eternal quiet. This is not a place of sadness or finality, but rather a serene garden of stellar memories, where the compressed essence of once mighty suns continues to exist in forms so dense and stable that they can persist for billions upon billions of years, patiently waiting for the right cosmic circumstances to stir them back to gentle activity. These cosmic cemeteries are scattered throughout every galaxy, invisible to casual observation, but revealed through the patient work of astronomers who have learned to detect the subtle signatures of stellar remnants. Unlike earthly cemeteries with their rows of markers and monuments, these stellar resting places are marked by objects so small and dim that they challenge our ability to perceive them, yet so dense and powerful that they represent some of the most extreme states of matter in the universe. The residents of these cosmic cemeteries come in several varieties, each representing a different path that a star might have taken at the end of its natural life. The most common inhabitants are white dwarf stars, the cooling remnants of stars that were not quite massive enough to end their lives in the spectacular explosions we call supernovas. These white dwarfs are like cosmic embers, slowly cooling objects about the size of Earth, but containing roughly the mass of our Sun, compressed into a state so dense that a teaspoon of white dwarf material would weigh as much as an automobile. Then there are the neutron stars, even more compressed remnants of slightly more massive stars that did experience the gentle violence of stellar death. These objects are so dense that they compress the mass of our Sun into a sphere only about 20 kilometers across, creating conditions so extreme that the very atoms are crushed beyond recognition, leaving behind a ball of pure neutron matter, the densest stable matter known to exist in the universe. The atmosphere of these cosmic cemeteries is one of profound peace and patience. Time moves differently here, measured not in human moments, but in cosmic epochs. A white dwarf might cool for billions of years without any significant change, existing in a state of perfect equilibrium between the inward pull of its own gravity and the outward pressure of degenerate matter. A quantum mechanical effect that prevents further collapse and maintains the star's integrity across unimaginable spans of time. The silence in these cosmic cemeteries is deeper than any earthly quiet. There are no sounds, of course, in the vacuum of space, but there's also an absence of the nuclear fires that once roared within these stellar cores. The fusion reactions that powered these stars for millions or billions of years have long since ceased, leaving behind only the slowly fading heat of their final moments of active stellar life. The cooling process is so gradual that these stellar remnants will remain warm by cosmic standards for longer than the current age of the universe. Yet this apparent lifelessness is deceptive, for these cosmic cemeteries are not places of permanent rest, but rather of patient waiting. The stellar remnants that populate these celestial gardens retain all the gravitational authority of their former selves, and in many cases, even more. Their compressed matter creates gravitational fields so intense that they can influence their surroundings across vast distances, pulling on any nearby matter with an inexorable but gentle persistence. The beauty of these cosmic cemeteries lies not in what they lack, but in what they preserve. Each white dwarf and neutron star is a library of stellar history, containing within its compressed matter the processed elements that were created during the star's active lifetime. The carbon and oxygen that make up most white dwarfs were forged in the nuclear furnaces of red giant stars. The exotic matter within neutron stars represents states of nuclear physics that cannot be replicated anywhere else in the universe. The landscape of a cosmic cemetery is defined by invisible forces and subtle influences. Gravitational fields bend space and time around each stellar remnant, creating wells of curved space-time that would be imperceptible to human senses but profound in their cosmic implications. Light passing near these objects is gently deflected. Time flows slightly slower in their vicinity, and the very fabric of space responds to their presence with a curvature that speaks to the fundamental unity of matter, energy, space, and time. In the spaces between these stellar remnants, the cosmic cemetery contains wisps of gas and dust, the diffuse remains of stellar atmospheres that were gently expelled during the final stages of stellar evolution. These tenuous clouds drift slowly through space, sometimes forming beautiful planetary nebulae around white dwarf stars, creating cosmic art galleries where the ghostly light of the central remnant illuminates delicate structures of glowing gas that can span light years in extent. The temperature in these cosmic cemeteries varies dramatically depending on the age and type of stellar remnant. Young white dwarfs can still glow with surface temperatures of tens of thousands of degrees, making them among the hottest objects in the galaxy, even though they are no longer generating energy through nuclear fusion. As they age, they cool slowly and steadily, their surface temperatures dropping over billions of years until they eventually fade to become cold, dark objects that are virtually impossible to detect. Neutron stars, despite their incredible density, can also vary widely in temperature and activity. Some are relatively quiet, cooling slowly like their white dwarf cousins. Others, particularly those that are part of binary systems or have strong magnetic fields, can display remarkable activity even millions of years after their formation. These more active neutron stars might emit beams of radiation that sweep across space like cosmic lighthouses, or they might heat their surfaces through the decay of exotic particles created in their ultradense cores. The magnetic environments in cosmic cemeteries can be extraordinary, particularly around neutron stars. These objects can possess magnetic fields trillions of times stronger than Earth's magnetic field, creating invisible structures that extend far into space around them. These magnetic fields can accelerate charged particles to tremendous speeds, creating phenomena that make these apparently dead stars some of the most energetic objects in the universe. The orbital mechanics within cosmic cemeteries often involve objects that have been gravitationally bound for billions of years. Binary systems consisting of two white dwarfs, or a white dwarf and a neutron star, can spiral around each other in perfectly choreographed dances that take centuries or millennia to complete a single orbit. These systems are laboratories for studying the extreme physics of dense matter and strong gravitational fields, and they represent some of the most stable dynamical systems in the universe. The chemical composition of cosmic cemeteries reflects the nuclear alchemy that took place within the original stars during their active lifetimes. White dwarfs are primarily made of carbon and oxygen, the ashes of helium burning that occurred in the cores of red giant stars. Some white dwarfs also contain significant amounts of neon, magnesium, or other elements, depending on the mass and composition of their progenitor stars. Neutron stars, being far more exotic, consist primarily of neutrons with a thin crust of more conventional atomic nuclei and a core that may contain exotic particles like hyperons or quark matter. The evolutionary timescales within cosmic cemeteries stretch far beyond human comprehension. A white dwarf will cool from its initial temperature of hundreds of thousands of degrees to near absolute zero over a period longer than 1 trillion years, a timescale that exceeds the current age of the universe by a factor of nearly 100. During this cooling process, the white dwarf will undergo various phase transitions as its crystalline structure changes, but these changes are so gradual that they represent the ultimate in cosmic patience. The gravity wells created by stellar remnants in cosmic cemeteries are not just empty depressions in space-time, but can become collection points for new material. Gas and dust drifting through the galaxy can be captured by the gravitational influence of white dwarfs and neutron stars, slowly accumulating in thin disks or diffuse halos around these objects. This process is usually so gradual that it takes millions or billions of years to accumulate significant amounts of material, but it represents the first step in what can eventually become stellar resurrection. The energy sources within cosmic cemeteries are subtle and varied. While nuclear fusion has ceased in these stellar remnants, other processes can still generate energy. The slow crystallization of white dwarf interiors releases gravitational potential energy that can keep these objects warm for billions of years. Neutron stars can generate energy through the decay of their magnetic fields, the friction of their rotation, or the decay of exotic particles in their cores. As you drift through this cosmic cemetery in your imagination, surrounded by the peaceful presence of stellar remnants that have found their eternal rest, let yourself appreciate the profound tranquility of these celestial spaces. Here, the frantic pace of stellar evolution has given way to cosmic contemplation, where time is measured in geological epochs and change happens so slowly that it approaches the eternal. These stellar remnants are not dead, but rather transformed, existing in states of matter so exotic and stable that they represent entirely new forms of cosmic existence. The beauty of cosmic cemeteries lies in their demonstration that endings can be beginnings, that the apparent death of a star is actually its transformation into something new and potentially more enduring than its original form. In this peaceful cosmic setting, we begin to understand how the universe provides opportunities for renewal and resurrection, setting the stage for the gentle awakenings that can stir these sleeping giants back to activity under the right circumstances. In the gentle stillness of your resting place, imagine witnessing the most graceful farewell in the universe, the final moments of a massive star's life, unfolding not with violence or chaos, but with the serene dignity of a cosmic giant that has completed its billion-year journey through stellar evolution. As you settle deeper into tranquility, we'll explore how these stellar titans reach the end of their active lives, not through sudden catastrophe, but through a gradual and inevitable process that represents one of nature's most patient and thorough transformations. The journey towards stellar death begins long before any visible signs appear to casual observers. Deep within the core of a massive star, nuclear processes that have sustained the star's luminosity for millions of years begin to reach their natural conclusion. The star has spent its lifetime fusing lighter elements into heavier ones, starting with hydrogen burning to create helium, then progressing through increasingly complex nuclear reactions that forge carbon, oxygen, neon, silicon, and finally iron. Each stage of this nuclear evolution has been slower than the last, as the star has had to burn its fuel at ever higher temperatures to maintain the delicate balance between gravitational collapse and radiation pressure. The creation of iron in the stellar core marks a cosmic turning point, though this moment unfolds over thousands of years rather than in any dramatic instant. Iron represents the peak of nuclear binding energy, the point at which nuclear fusion can no longer release energy to support the star structure. When a star begins producing significant amounts of iron in its core, it has reached the end of its ability to generate energy through nuclear burning. The star doesn't immediately recognize this cosmic milestone, continuing to burn and fuse elements in its outer layers while the iron core grows slowly and inexorably at its center. This iron core accumulation is like the gradual settling of sediment in a cosmic lake, building up layer by layer until it reaches a critical mass. The process is remarkably patient and methodical, with the star maintaining its external appearance and luminosity even as its fundamental energy source approaches exhaustion. The outer layers of the star continue their nuclear burning, creating a complex onion-like structure with different elements being fused at different distances from the center. The temperature and pressure conditions within the dying star's core become more extreme than anywhere else in the ordinary universe. Temperatures rise to billions of degrees, while pressures reach levels where atomic nuclei are crushed together with incredible force. Under these conditions, matter begins to behave in ways that seem almost magical, with electrons being pressed into protons to form neutrons and neutrinos. The star is essentially transforming itself from the inside out, converting ordinary atomic matter into increasingly exotic forms. As the iron core grows, it begins to approach the Chandrasekhar limit, a critical mass beyond which the quantum mechanical forces that support the core against gravitational collapse can no longer maintain equilibrium. This limit, approximately 1.4 times the mass of our Sun, represents a fundamental threshold in stellar physics. When the core approaches this mass, the star enters its final phase of active existence, though this phase can still last for thousands of years as the core slowly accumulates the final material needed to trigger collapse. The stellar atmosphere during this final phase often becomes unstable and begins to pulsate gently, like the slow breathing of a cosmic giant preparing for rest. These pulsations can cause the star to vary its brightness over periods of months or years, as different layers expand and contract in response to the changing energy output from the core. The star might shed some of its outer material during these pulsations, creating beautiful nebular structures that will eventually become part of the interstellar medium. The moment of core collapse, when it finally occurs, happens with stunning swiftness on cosmic scales. The iron core, having finally exceeded its ability to support itself against gravity, begins to contract. What had taken millions of years to build up collapses in less than a second, with the core shrinking from the size of Earth to a sphere only 20 kilometers across. This collapse is so rapid and complete that it represents one of the most dramatic transformations possible in the physical universe. But even this moment of ultimate stellar transformation maintains an element of cosmic grace. The collapse is not chaotic or random, but follows precise physical laws that govern the behavior of matter under extreme conditions. The infalling material rebounds when it encounters the incredibly dense neutron matter at the core center, creating a shock wave that propagates outward through the star. This shock wave carries with it the energy needed to disrupt the star's outer layers and create the spectacular phenomenon we observe as a supernova explosion. The supernova itself, while appearing violent from a distance, serves a profoundly creative purpose in the cosmic ecosystem. The explosion disperses the heavy elements that were created during the star's lifetime, enriching the interstellar medium with carbon, oxygen, silicon, iron, and other elements essential for planet formation and eventually life itself. The shock wave also compresses nearby gas clouds, potentially triggering the formation of new stars. In this way, stellar death becomes a catalyst for stellar birth, completing a cosmic cycle of renewal and regeneration. The energy released during a supernova is almost incomprehensibly vast, equivalent to the total energy output of our sun over its entire 10 billion-year lifetime, released in just a few seconds. Yet this enormous energy release serves the gentle purpose of cosmic recycling, ensuring that the elements created during stellar nucleosynthesis are returned to the galaxy for use in future generations of stars and planets. The explosion is not destructive, but distributive, spreading stellar wealth throughout the cosmic neighborhood. The visual spectacle of a supernova, while dramatic, unfolds over weeks and months rather than in any sudden flash. The explosion begins in the star's core, but takes time to propagate outward through the star's massive bulk. Observers might first notice the star brightening gradually, then maintaining peak luminosity for several weeks before slowly fading over months or years. This extended timeline allows the dying star to make a prolonged farewell, visible across vast distances as a testament to its cosmic significance. The neutrinos produced during the core collapse provide a fascinating window into the dying star's final moments. These nearly massless particles, which interact so weakly with matter that they can pass through entire planets without being affected, carry information directly from the collapsing core. Billions of neutrinos stream outward from the dying star, racing ahead of the light from the explosion and providing astronomers with an early warning system for detecting stellar death in real time. The elements created during the supernova explosion include some of the heaviest and most exotic atoms in the periodic table. The intense neutron flux during the explosion can create elements that are impossible to forge during normal stellar burning, including gold, platinum, uranium, and other heavy elements that require rapid neutron capture processes. These precious metals, literally forged in the dying moments of massive stars, will eventually become incorporated into planets and potentially into living organisms. The shock waves from supernovas travel through the interstellar medium for thousands of years, creating beautiful and complex structures known as supernova remnants. These expanding shells of hot gas and magnetic fields can span hundreds of light years and serve as cosmic laboratories for studying high-energy physics. The shock waves also play important roles in heating and stirring the interstellar medium, contributing to the complex ecology of galactic evolution. The magnetic fields generated during stellar collapse can become trapped and amplified in the resulting neutron star, creating some of the strongest magnetic fields known in the universe. These fields, trillions of times stronger than Earth's magnetic field, create complex structures around the neutron star and can accelerate particles to tremendous energies. The interaction between these magnetic fields and the neutron star's rotation can create lighthouse-like beams of radiation that sweep across space as the star spins. Not all massive stars end their lives in supernova explosions. Stars that are particularly massive, more than about 25 times the mass of our sun, may undergo direct collapse to form black holes without producing a visible explosion. Even in these cases, the stellar death is not violent, but represents the ultimate surrender to gravity's inexorable pull. The star simply fades from view as its matter disappears behind the event horizon, leaving behind only its gravitational influence on the surrounding space. The timing of stellar death depends on the star's initial mass, with more massive stars living shorter but more spectacular lives. A star like our Sun will shine steadily for about 10 billion years before gradually expanding into a red giant and eventually becoming a white dwarf. Stars with 10 times the Sun's mass might live for only 20 million years before ending in supernova explosions. The most massive stars of all might burn through their nuclear fuel in just a few million years, living fast and dying young in cosmic terms. The final moments before collapse are characterized by increasingly rapid nuclear burning as the star desperately attempts to maintain equilibrium against gravitational contraction. Silicon burning in the core can consume the star's remaining nuclear fuel in just a few days, while the final iron core formation happens over a matter of hours. These accelerating timescales reflect the star's increasing desperation to maintain the nuclear fires that have sustained it throughout its lifetime. The stellar winds that precede supernova explosions can be remarkably powerful, carrying away significant portions of the star's mass in the years leading up to core collapse. These winds create complex structures in the space around the dying star, forming shells and bubbles of gas that will later interact dramatically with the supernova shock wave. The interaction between the explosion and these pre-existing structures creates some of the most beautiful and complex astronomical objects in the universe. The rotation of the dying star plays a crucial role in determining the final outcome of stellar collapse. Rapidly rotating stars may form neutron stars with millisecond spin periods, while slowly rotating stars produce more conventional pulsars. The conservation of angular momentum during collapse means that even a slowly rotating massive star can produce a neutron star that spins dozens of times per second, converting the star's leisurely rotation into rapid neutron star spinning. The chemical composition of the dying star's outer layers determines what elements will be dispersed into space during the supernova explosion. Stars that have undergone significant mass loss during their lifetimes may have exposed their helium or carbon-rich inner layers, leading to explosions that disperse unusual combinations of elements. This chemical diversity ensures that each supernova makes its own unique contribution to the galactic inventory of heavy elements. As the massive star approaches its final moments, it has become a cosmic time bomb in the most gentle sense. Not a device of destruction, but an instrument of cosmic renewal waiting to distribute its accumulated nuclear wealth to the galaxy. The star has spent its entire lifetime preparing for this moment of ultimate generosity, converting simple hydrogen into the complex elements needed for planets, life, and consciousness. Its death will be its greatest gift to the universe, ensuring that the heavy elements locked within its core can participate in future cosmic evolution. The gravitational waves produced during stellar collapse and supernova explosions represent ripples in the fabric of space-time itself, carrying information about the dying star's final moments at the speed of light. These waves, recently detected for the first time by advanced interferometers on Earth, provide a new way of studying stellar death and the extreme physics of neutron star formation. The waves carry energy away from the collapsing core, helping to power the supernova explosion while creating disturbances in space-time that can be detected across cosmic distances. As you rest in the peaceful comfort of your evening sanctuary, let this vision of stellar death wash over you like the gentlest of cosmic tides. The dying giants of the universe approach their final moments not with fear or violence, but with the serene dignity of cosmic citizens who have completed their appointed roles in the grand symphony of stellar evolution. Their deaths are not endings, but transformations, not failures, but fulfillments of their cosmic purpose. In their final breath, these stellar giants demonstrate that even the most dramatic changes in the universe can unfold with grace, patience, and profound beauty. In the profound stillness of your resting space, imagine witnessing the most extraordinary compression in the universe, a process so gentle yet so complete that it transforms matter itself into entirely new states of existence. As you settle deeper into tranquility, we'll explore the remarkable phenomenon of stellar core collapse, a transformation that happens with such precision and elegance that it represents one of physics' most beautiful demonstrations of how extreme conditions can create rather than destroy, how ultimate compression can lead to ultimate stability. The collapse of a stellar core begins at the moment when the iron heart of a massive star can no longer support itself against the inexorable pull of its own gravity. This moment arrives not with sudden violence, but as the natural conclusion of millions of years of stellar evolution, like the final note in a cosmic symphony that has been building toward this crescendo throughout the star's entire lifetime. The iron core, having reached the critical mass known as the Chandrasekhar limit, finds itself in a state where the quantum mechanical forces that have supported it can no longer balance the gravitational forces trying to compress it further. The initial phase of collapse happens with stunning swiftness, yet follows laws of physics so precise that every aspect of the process unfolds according to mathematical relationships that govern the behavior of matter under extreme conditions. The core, which had been roughly the size of Earth with a mass greater than our Sun, begins to contract under its own gravity. What makes this collapse so remarkable is not its speed, though it happens faster than any other natural process, but its orderliness. Matter doesn't fall chaotically inward, but follows streamlined paths determined by the geometry of space-time itself. As the collapse proceeds, the density of matter within the core increases by factors that challenge human comprehension. Atomic nuclei, which had maintained their distinct identities throughout the star's lifetime, begin to merge and transform as they are pressed together with forces greater than those found anywhere else in the universe. The electrons that had orbited these nuclei are squeezed with such pressure that they combine with protons to form neutrons, releasing neutrinos in a process that represents one of the most efficient energy conversions known to physics. The temperature within the collapsing core rises to levels that dwarf even the nuclear furnaces that powered the star during its active lifetime. These temperatures, measured in tens of billions of degrees, create conditions where the normal rules of chemistry cease to apply and matter exists in states that can only be described through the most advanced theories of nuclear physics. Yet even under these extreme conditions, the collapse maintains its orderly character, following precise mathematical laws that ensure the process unfolds smoothly and predictably. The pressure within the collapsing core reaches values that exceed the pressure at the center of atomic nuclei by factors of millions. Under these conditions, matter undergoes a phase transition more dramatic than any change of state we observe in everyday life. The familiar particles that make up ordinary matter, protons, neutrons, and electrons, are transformed into exotic forms that exist nowhere else in the universe. The core becomes a laboratory for studying the fundamental properties of matter under conditions that cannot be replicated by any earthly experiment. As the core contracts, it approaches nuclear density, the density at which matter is packed as tightly as it is within atomic nuclei. When the core reaches this critical density, something remarkable happens. The nuclear force that binds protons and neutrons together within atomic nuclei begins to resist further compression. This resistance creates a kind of cosmic cushion that halts the inward collapse and causes the infalling material to rebound outward, like a compressed spring suddenly released. The rebound that occurs when the core reaches nuclear density is one of the most energetic events in the universe, yet it happens with mathematical precision rather than chaotic violence. The shock wave that forms at the boundary between the ultra-dense core and the still infalling outer layers carries more energy than our sun will produce in its entire lifetime. But this energy is channeled according to the laws of hydrodynamics and thermodynamics in ways that ensure the process unfolds smoothly and efficiently. The newly formed neutron star that emerges from this collapse represents a triumph of quantum mechanics over classical physics. The object that results from the collapse is supported not by thermal pressure or chemical forces, but by the quantum mechanical principle known as neutron degeneracy pressure. This exotic form of support allows the neutron star to maintain a stable configuration that is more compact and more perfectly spherical than any other known type of matter in the universe. The material composition of a newly formed neutron star stretches the boundaries of our understanding of matter itself. The surface consists of a thin atmosphere of light elements, below which lies a crust of heavy atomic nuclei arranged in a crystalline lattice of unprecedented regularity. Deeper within the neutron star, atomic nuclei dissolve entirely, giving way to a fluid of pure neutron matter that flows without friction or resistance. At the very center, conditions may be so extreme that neutrons themselves break down into their constituent quarks, creating forms of matter that have never been observed anywhere else. The magnetic field that emerges from a newly formed neutron star can be trillions of times stronger than Earth's magnetic field. Yet this incredible field's strength develops not through any violent process, but as a natural consequence of the conservation of magnetic flux during the collapse. As the stellar core contracts, any magnetic field lines that were present in the original star are compressed along with the matter, concentrating the magnetic field into a space billions of times smaller than its original volume. The rotation of a newly formed neutron star often exceeds anything observed elsewhere in the universe, with some neutron stars spinning hundreds of times per second. This rapid rotation arises from the conservation of angular momentum during the collapse. As the stellar core contracts, its rotation rate increases in the same way that an ice skater spins faster when pulling in their arms. The result is an object that can complete a full rotation in milliseconds while maintaining perfect stability and balance. The gravitational field around a newly formed neutron star is so intense that it significantly warps the fabric of space-time itself. Time runs measurably slower at the neutron star's surface than it does in the surrounding space, and light emitted from the surface is redshifted to longer wavelengths as it climbs out of the star's gravitational well. These effects, predicted by Einstein's general theory of relativity, transform the neutron star into a natural laboratory for studying the relationship between gravity, space, and time. The cooling process that begins immediately after neutron star formation represents one of the most gradual and patient transformations in the universe. The newly formed neutron star starts with a core temperature of hundreds of billions of degrees, but it cools by radiating neutrinos and photons into space over billions of years. This cooling process is so slow and steady that astronomers can use the temperature of a neutron star to estimate how long ago it was formed, turning each neutron star into a cosmic timepiece that records the history of stellar death in its galaxy. The seismic activity within a neutron star creates phenomena unlike anything found on any other type of celestial body. The crystalline crust of a neutron star can occasionally crack under the immense stresses created by the star's rotation and magnetic field, producing starquakes that release more energy than the largest earthquakes on Earth. Yet, even these dramatic events maintain the neutron star's overall stability and represent natural adjustments that help the star maintain its equilibrium configuration. The equation of state that governs matter at nuclear densities remains one of the great unsolved problems in physics, making each neutron star a unique experiment in extreme matter physics. The behavior of matter under these conditions cannot be fully predicted by current theories, so every observation of neutron star properties provides new insights into the fundamental nature of matter itself. These stellar remnants serve as natural laboratories where physicists can test their understanding of nuclear and particle physics under conditions that are impossible to create on Earth. The moment of neutron star formation represents a cosmic phase transition comparable to the freezing of water or the condensation of steam, but occurring under conditions so extreme that entirely new states of matter emerge. This phase transition happens not gradually, but almost instantaneously on cosmic scales, as the stellar core transforms from ordinary matter to neutron matter in less than a second. The precision and completeness of this transformation demonstrate the underlying order and mathematical beauty that governs even the most extreme physical processes. The neutron star that emerges from stellar collapse is not just a compressed version of the original stellar core, but a fundamentally new type of object with properties that were impossible in the original star. The neutron star is more stable than the original star, more compact, more perfectly spherical, and more magnetically active. In many ways, the collapse process has not destroyed the star, but has refined it, creating a more perfect and more enduring form of stellar existence. The energy budget of stellar collapse reveals the incredible efficiency of this natural process. Nearly all of the gravitational potential energy released during the collapse goes into creating neutrinos, which carry this energy away from the neutron star at the speed of light. This energy release is so enormous that a single stellar collapse produces more neutrinos than all the stars in the observable universe combined emit through normal stellar burning. Yet this tremendous energy release serves the constructive purpose of removing excess heat from the newly formed neutron star. allowing it to settle into a stable configuration. The timescales involved in neutron star formation span an enormous range, from the millisecond duration of the initial collapse to the billion-year cooling process that follows. This range of timescales reflects the different physical processes involved, from the rapid gravitational dynamics that drive the collapse to the slow thermal evolution that governs the neutron star's subsequent development. Each phase of neutron star formation operates according to its own characteristic timescale, creating a complex temporal symphony of physical processes. The structural perfection achieved through stellar collapse is remarkable for its geometric precision. Neutron stars are among the most perfectly spherical objects in the universe, with surface irregularities typically no more than a few millimeters on objects that are 20 kilometers in diameter. This incredible smoothness results from the immense gravitational field, which smooths out any irregularities that might have existed in the original stellar core. The relationship between mass and radius in neutron stars follows a universal curve that depends only on the fundamental properties of nuclear matter, making these objects natural standards for measuring the most basic constants of physics. The fact that neutron stars with very different histories all follow the same mass-radius relationship demonstrates the underlying universality of physical laws and the inevitability of the final configurations that result from stellar collapse. The interior structure of a neutron star reveals layers of increasingly exotic matter arranged in perfectly concentric shells, like a cosmic onion made of the most extreme materials in the universe. Each layer has its own characteristic density, composition, and physical properties, yet all layers work together to create a stable, self-supporting structure. The smooth variation of density from the surface to the core ensures that the neutron star exists in perfect hydrostatic equilibrium, balance between the inward pull of gravity and the outward pressure of degenerate matter. As you rest in the gentle darkness of your room, let this vision of gentle collapse wash over you like the softest of cosmic tides. The transformation of a stellar core into a neutron star represents one of nature's most elegant solutions to the challenge of extreme density, showing us that even under the most extreme conditions, matter can find stable, beautiful, and enduring configurations. This cosmic compression creates rather than destroys, bringing into existence forms of matter that are more perfect and more stable than anything possible under ordinary conditions. The gentle collapse teaches us that transformation, even radical transformation, can unfold with grace, precision, and profound beauty, creating something new and wonderful from what came before. In the serene quiet of your evening sanctuary, imagine a cosmic sleeping beauty, a stellar remnant that has rested peacefully for millions or even billions of years, cooling slowly in the depths of space, its nuclear fires long extinguished. Yet unlike fairy tale slumber, this cosmic sleep is not permanent, for under the right circumstances, these stellar remnants can be gently awakened to shine once more. As you settle deeper into comfort, we'll explore the beautiful phenomenon of white dwarf resurrection, where the patient accumulation of material can slowly stir these sleeping stars back to active life. White dwarf stars represent the final evolutionary stage for the vast majority of stars in the universe, including our own Sunday. These stellar remnants are the compressed cores of stars that were not massive enough to end their lives in supernova explosions, instead undergoing a more gentle transition from active star to stellar corpse. A white dwarf contains roughly the mass of our Sun compressed into a sphere about the size of Earth, creating matter so dense that a teaspoon of white dwarf material would weigh as much as an automobile, yet so stable that it can persist unchanged for longer than the current age of the universe. The surface of a newly formed white dwarf glows with temperatures that can exceed 100,000 degrees Celsius, making it one of the hottest objects in the galaxy despite no longer generating energy through nuclear fusion. This heat is simply the leftover thermal energy from the star's active lifetime, slowly radiating away into space over billions of years. The white dwarf is like a cosmic ember, gradually cooling from white-hot through yellow, red, and eventually to a cold, dark state that astronomers call a black dwarf. Though the universe is not yet old enough for any white dwarfs to have completed this cooling process. The awakening of a white dwarf requires a cosmic partnership, for these stellar remnants lack the ability to restart their nuclear fires on their own. The key to resurrection lies in the white dwarf's powerful gravitational field, which can capture material from a nearby companion star if the two objects orbit close enough together. This process of stellar cannibalism is not violent or sudden, but unfolds with the patience of cosmic time, as material slowly spirals inward from the donor star toward the hungry white dwarf. The journey of material from companion star to white dwarf begins when the gravitational influence of the compact object starts to distort the shape of its partner. Stars are normally spherical, held in perfect balance by the equilibrium between gravitational collapse and radiation pressure. But when a white dwarf orbits close enough to another star, its intense gravitational field creates tidal forces that stretch the companion star into an elongated shape, like the way Earth's gravity creates tides in our oceans, but on a vastly larger scale. As the companion star becomes distorted by these tidal forces, material from its outer layers begins to stream toward the white dwarf. This transfer of material doesn't happen all at once, but represents a gradual process that can continue for millions or billions of years. The donated material doesn't fall directly onto the white dwarf surface, but instead forms an elegant spiral structure called an accretion disk, where the infalling matter orbits the white dwarf in ever-decreasing circles before finally reaching the stellar surface. The accretion disk that forms around a white dwarf is one of the most beautiful and dynamic structures in the universe, resembling a cosmic whirlpool made of superheated gas. The material in the disk glows with temperatures of tens of thousands of degrees as gravitational compression and friction heat it to incandescence. The disk can extend for millions of kilometers around the white dwarf, creating a luminous spiral that outshines the white dwarf itself and makes the entire system visible from vast distances. The behavior of matter within the accretion disk follows the elegant laws of fluid dynamics and thermodynamics, creating patterns and structures that demonstrate the underlying mathematical beauty of physical processes. Spiral density waves propagate through the disk like cosmic versions of the arms of a spiral galaxy, while magnetic fields thread through the hot gas and help channel material toward the white dwarf's magnetic poles. The disk exhibits a complex interplay of rotation, turbulence, and magnetic activity that creates a constantly changing display of cosmic artistry. The rate at which material accumulates on the white dwarf surface is typically very slow by human standards, often amounting to only a few Earth masses over millions of years. This gradual accumulation allows the white dwarf to slowly gain mass while maintaining its structural stability. The newly acquired material settles onto the white dwarf surface in a thin layer, where it is compressed by the star's intense gravity and heated by the energy of impact to temperatures of millions of degrees. As this layer of accreted material builds up over time, it undergoes a gradual transformation from ordinary stellar material to the degenerate matter that characterizes white dwarf interiors. The intense pressure and temperature at the white dwarf surface compress the newly arrived atoms into a crystalline lattice structure, creating some of the most perfectly ordered matter in the universe. This process is like cosmic geology, with new layers of exotic matter being deposited on the white dwarf surface over vast periods of time. The chemical composition of the accreted material plays a crucial role in determining how the white dwarf will respond to its gradual mass gain. Material rich in hydrogen will behave differently from material composed primarily of helium or heavier elements. The nuclear processes that can occur in the accreted layer depend on both the composition of the material and the temperature and pressure conditions at the white dwarf surface, which in turn depend on the mass and age of the white dwarf itself. When the accumulated material reaches a critical mass, typically after millions of years of patient accumulation, the white dwarf begins to show signs of awakening from its long slumber. The temperature and pressure in the accreted layer reach levels where nuclear fusion can once again ignite, marking the first time in millions of years that the stellar remnant has generated energy through nuclear burning. This rekindling of nuclear fires represents a genuine resurrection, transforming the cold stellar corpse back into an active, energy-producing star. The nuclear burning that occurs in the accreted layer is different from the fusion processes that powered the original star during its main sequence lifetime. The extreme conditions on the white dwarf surface create a runaway nuclear reaction that burns through the accumulated material in a matter of hours or days, releasing enormous amounts of energy in a brief but spectacular outburst. This explosion, known as a nova, can increase the white dwarf's brightness by factors of thousands or even millions, making it visible from across the galaxy. The nova explosion represents not destruction but renewal, as the white dwarf sheds its accumulated material in an expanding shell of hot gas while retaining its essential structure and mass. The explosion clears away the layer of accreted material, returning the white dwarf to its previous quiescent state, but the process can repeat whenever enough new material accumulates on the surface. Some white dwarfs undergo nova explosions regularly, becoming recurrent novae that brighten and fade on predictable schedules spanning decades or centuries. The energy released during a nova explosion comes primarily from the nuclear fusion of hydrogen into helium, the same process that powers ordinary stars, but occurring under the extreme conditions present on a white dwarf surface. The explosion converts a tiny fraction of the accreted matter into energy according to Einstein's famous equation, E equals mc squared, demonstrating that even small amounts of matter can produce enormous energy releases when the conditions are right. The expanding shell of gas ejected during a nova explosion creates some of the most beautiful structures in the universe, forming intricate patterns of glowing gas that can persist for thousands of years after the explosion. These nova remnants, illuminated by the continuing radiation from the central white dwarf, create cosmic art galleries where the interplay of gas dynamics, radiation, and magnetic fields produces ever-changing displays of celestial beauty. The white dwarf that emerges from a nova explosion is essentially unchanged by the experience, retaining its mass, structure, and fundamental properties. The explosion has cleared away the accumulated material that triggered the outburst, but the white dwarf's gravitational field continues to attract material from its companion star, setting the stage for future accumulation and eventual reawakening. This cyclical process can repeat hundreds or thousands of times over the white dwarf's lifetime, making it a renewable source of stellar energy. The observational signatures of awakening white dwarfs provide astronomers with unique laboratories for studying extreme physics and stellar evolution. The brightness variations during nova explosions can be monitored in real time, allowing researchers to study the nuclear physics of stellar surfaces and the dynamics of explosive stellar atmospheres. The spectral lines observed during nova explosions reveal the chemical composition of both the white dwarf and its companion star, providing insights into stellar nucleosynthesis and galactic chemical evolution. The discovery of white dwarf resurrection has revolutionized our understanding of stellar evolution and the ways that stars can return to active life after apparent death. These zombie stars demonstrate that stellar evolution is not a one-way process leading inevitably to cold, dark stellar corpses, but rather a complex cycle where stellar remnants can find new sources of energy and new ways to shine. The resurrection process shows that partnerships between stars can extend stellar lifetimes far beyond what would be possible for isolated objects. The variety of white dwarf awakening scenarios reflects the diversity of stellar partnerships possible in the universe. Some white dwarfs gradually accumulate material from slowly evolving companion stars over billions of years, while others experience rapid mass transfer from companions that are undergoing their own evolutionary changes. The timing and characteristics of white dwarf resurrection depend on the orbital properties of the binary system, the masses of both stars, and their evolutionary histories. The ultimate fate of a white dwarf undergoing repeated resurrection cycles depends on whether it gains or loses mass over time. If the white dwarf accumulates more material than it ejects during nova explosions, it may gradually approach the critical mass limit that determines its stability. If it reaches this limit, known as the Chandrasekhar mass, the white dwarf may undergo a final, catastrophic explosion that completely destroys the star in what astronomers call a type I supernova. The potential for white dwarf destruction through excessive mass gain adds an element of cosmic drama to the resurrection process, though even this ultimate fate serves a constructive purpose in the cosmic ecosystem. Type I supernovae are among the most important sources of heavy elements in the universe, particularly iron and related elements that are essential for planet formation and biological processes. The destruction of an overfed white dwarf represents the ultimate act of cosmic generosity, distributing accumulated stellar material throughout the galaxy. The study of white dwarf resurrection has also provided insights into the role of stellar remnants in the chemical evolution of galaxies. The nova explosions that mark each awakening episode eject processed nuclear material into the interstellar medium, contributing to the gradual enrichment of the galaxy with heavy elements. Over billions of years, the cumulative effect of countless white dwarf awakenings helps to increase the chemical complexity of the galactic environment, creating the conditions necessary for planet formation and the emergence of life. The magnetic fields of white dwarfs play important roles in controlling how accreted material reaches the stellar surface and how nova explosions develop. Some white dwarfs possess magnetic fields millions of times stronger than Earth's magnetic field, strong enough to channel the flow of accreted material and create localized hot spots on the stellar surface. These magnetic effects can influence the timing and characteristics of nova explosions, creating variations in brightness and spectral properties that reflect the complex interplay between gravity, nuclear physics, and magnetism. The rotation of white dwarfs also influences their resurrection behavior, with rapidly spinning white dwarfs sometimes showing different patterns of mass accumulation and nuclear burning than their more slowly rotating cousins. The centrifugal forces created by rapid rotation can affect the stability of the accreted layer and the propagation of nuclear burning across the stellar surface, creating variations in nova properties that help astronomers understand the detailed physics of these explosive events. As you rest in the peaceful comfort of your room, let this vision of awakening white dwarfs wash over you like the gentlest of cosmic dawns. These sleeping stellar giants demonstrate that rest is not permanent, and that even apparent death can be overcome through cosmic partnership and patience. The white dwarf resurrections remind us that the universe provides opportunities for renewal and second chances, that stellar death can be transformed into stellar rebirth through the gentle accumulation of material and the patient work of gravitational forces. In their cyclical awakenings, these zombie stars show us that endings can become beginnings, that cosmic partnerships can extend existence far beyond what seemed possible, and that the universe is filled with opportunities for beautiful, peaceful transformation. In the gentle tranquility of your evening rest, imagine the most refined dinner party in the universe, one that unfolds not over hours, but across millions of years, where the guest of honor is a stellar remnant that dines with cosmic patience on the material provided by its generous companion. As you settle deeper into peace, we'll explore the elegant process of stellar mass transfer, a cosmic feast so gradual and so carefully orchestrated that it represents one of nature's most sophisticated examples of shared sustenance and mutual benefit. The cosmic feast begins with the formation of a binary star system, where two stars are born close enough together that their gravitational fields bind them into an eternal orbital dance. These stellar partnerships are remarkably common in the universe, with more than half of all stars belonging to binary or multiple star systems. The two stars begin their lives as independent entities, each burning its own nuclear fuel and following its own evolutionary path, yet connected by the invisible threads of gravitational attraction that will ultimately determine both of their fates. As the more massive star in the binary system evolves more rapidly than its smaller companion, it eventually reaches the end of its nuclear burning lifetime and transforms into a stellar remnant. perhaps a white dwarf, neutron star, or even a black hole. This transformation occurs while the companion star continues its own slower evolutionary journey, creating a cosmic odd couple where one partner has completed its stellar evolution while the other remains in the prime of its stellar life. This asymmetric evolution sets the stage for the patient feast that will unfold over the eons to come. The gravitational relationship between the stellar remnant and its living companion creates one of the most elegant examples of celestial mechanics in the universe. The two objects orbit their common center of mass in paths that are determined by the precise balance between gravitational attraction and orbital motion. These orbits can be circular or elliptical, close or distant, and can evolve over time as the system loses energy through various processes. The orbital dance between the two objects creates a cosmic choreography that will determine when and how the mass transfer process begins. The initiation of mass transfer requires the living star to expand beyond a critical boundary known as its Roche lobe, an imaginary surface that defines the region of space where material is gravitationally bound to that particular star. As stars age and evolve, they often undergo periods of expansion where their outer layers swell outward. When the expanding star reaches the size of its Roche lobe, material from its outer atmosphere begins to feel the gravitational influence of the compact companion more strongly than the pull of its own stellar core. The moment when material first begins to flow from the donor star to the compact companion marks the beginning of the cosmic feast, though this moment arrives so gradually that it's more like the slow opening of a celestial floodgate than any sudden rupture. The initial mass transfer rate might be incredibly small, perhaps only a few grams per second, but this tiny trickle of stellar material represents the start of a process that can continue for millions or billions of years, gradually transforming both members of the binary system. The path that material takes as it flows from donor star to compact companion follows the gravitational topology of the binary system, creating streamlined flows that demonstrate the underlying mathematical beauty of celestial mechanics. The material doesn't simply fall straight across the space between the two stars, but instead follows curved trajectories that reflect the complex interplay of gravitational forces, rotational effects, and conservation of angular momentum. These material streams create elegant arcs and spirals that trace out the hidden geometry of the gravitational field. As the transferred material approaches the compact companion, it cannot simply fall directly onto the surface because it carries too much angular momentum from its origin in the rapidly rotating donor star. Instead, the material must shed this excess angular momentum through a process that creates one of the most beautiful structures in the universe, the accretion disk. This disk forms as the incoming material settles into a series of concentric orbits around the compact object, with each orbit representing a different energy level in the gravitational potential well. The accretion disk that forms around the compact companion is a masterpiece of fluid dynamics and thermodynamics, where the principles of physics create patterns and structures of remarkable beauty and complexity. The disk typically extends from very close to the compact object's surface out to distances comparable to the orbital separation of the binary system. Within this disk, material orbits the central object while slowly spiraling inward under the influence of viscous forces that cause neighboring rings of material to exchange angular momentum. The temperature structure within the accretion disk creates a gradient that ranges from millions of degrees near the inner edge to thousands of degrees at the outer regions. This temperature variation causes different parts of the disk to emit light at different wavelengths, creating a rainbow of colors that span the entire electromagnetic spectrum from radio waves to X-rays. The inner regions of the disk can be so hot that they outshine the surfaces of both stars in the binary system, making the accretion disk the dominant source of light and energy. The magnetic fields that thread through the accretion disk add another layer of complexity and beauty to the mass transfer process. These fields, which can be generated by the compact object itself or by dynamo processes within the flowing gas, create invisible structures that guide and channel the movement of charged particles within the disk. Magnetic field lines can become twisted and tangled by the differential rotation of the disk, storing energy that can be suddenly released in explosive events that add variability and excitement to the otherwise steady process of mass transfer. The rate at which material flows through the accretion disk and ultimately reaches the surface of the compact companion is determined by a delicate balance of physical processes, including viscosity, magnetic fields, radiation pressure, and gravitational torques. This accretion rate can vary dramatically over time, sometimes remaining steady for years or decades, other times showing rapid fluctuations that cause the brightness of the system to change on timescales of minutes or hours. These variations create a kind of cosmic heartbeat that reflects the underlying dynamics of the mass transfer process. The chemistry of the transferred material tells a story of stellar evolution and nuclear processing that spans the entire lifetime of the donor star. Material flowing from the surface layers of the donor star carries with it the products of nuclear burning that occurred deep within the stellar core during earlier phases of evolution. Elements like carbon, nitrogen, and oxygen that were created through stellar nucleosynthesis become incorporated into the accretion disk and eventually onto the surface of the compact companion, creating a chemical archaeological record of the donor star's evolutionary history. The interaction between the material stream and the accretion disk creates some of the most dynamic and variable phenomena observed in binary star systems. The point where the stream impacts the outer edge of the disk, known as the hot spot, can become a source of intense radiation and rapid variability. This hot spot rotates around the disk with the orbital period of the binary system, creating periodic variations in brightness that allow astronomers to measure the orbital properties of systems that are too distant to resolve spatially. The evolution of the mass transfer process depends on how the donor star responds to the loss of material from its outer layers. In some cases, the mass loss causes the star to shrink slightly, moving its surface back within its Roche lobe and temporarily halting the transfer process. In other cases, the star may continue to expand even as it loses mass, maintaining contact with its Roche lobe and sustaining the mass transfer over long periods. The specific evolutionary path depends on the mass and evolutionary state of the donor star, creating a rich variety of possible outcomes. The feedback between mass transfer and stellar evolution creates a complex dance where each partner in the binary system influences the evolution of the other. The donor star loses mass and may have its evolution accelerated or altered by the mass loss process. The compact companion gains mass and may experience changes in its structure, rotation, or magnetic field as a result of the accretion process. These mutual influences can lead to evolutionary paths that would be impossible for isolated stars, demonstrating the creative power of stellar partnerships. The timescales involved in the cosmic feast span an enormous range, from the orbital periods of minutes or hours that govern the dynamics of close binary systems to the evolutionary timescales of millions or billions of years over which the mass transfer process unfolds. The accretion disk itself can respond to changes on timescales ranging from seconds to years, while the overall evolution of the binary system proceeds on the leisurely pace of stellar evolution. This hierarchy of timescales creates a complex temporal symphony where rapid variations are superimposed on slower evolutionary trends. The efficiency of the mass transfer process depends on how much of the material that leaves the donor star actually reaches the surface of the compact companion. In some systems, a significant fraction of the transferred material may be ejected from the system entirely, carried away by stellar winds or explosive events within the accretion disk. This mass loss from the binary system can affect its orbital evolution and determine the ultimate fate of both stellar components. The observational consequences of the cosmic feast make these binary systems some of the most interesting and variable objects in the sky. The accretion disk can produce continuous emission across the electromagnetic spectrum, while episodic events like dwarf nova explosions or X-ray bursts create dramatic brightness variations that can increase the system's luminosity by factors of hundreds or thousands. These variations make accreting binary systems excellent laboratories for studying extreme physics and stellar evolution in real time. The role of the cosmic feast in galactic ecology extends far beyond the individual binary system to influence the chemical and energetic evolution of entire galaxies. The processed material ejected from accreting systems contributes to the interstellar medium, while the high-energy radiation produced by accretion disks can ionize and heat surrounding gas clouds. Over cosmic time, the cumulative effect of countless stellar feasts helps to drive the complex processes that govern galactic evolution and star formation. The diversity of cosmic feasts reflects the variety of possible combinations of stellar types, masses, and evolutionary states in binary systems. Systems containing white dwarfs, neutron stars, or black holes as the compact component each show characteristic signatures and behaviors. The mass and evolutionary state of the donor star also play crucial roles in determining the nature and timescale of the mass transfer process. This diversity ensures that no two cosmic feasts are exactly alike, each representing a unique chapter in the story of stellar evolution. The stability of the mass transfer process can vary dramatically between different types of binary systems. Some systems maintain steady, stable accretion for millions of years, while others undergo dramatic instabilities that can lead to explosive outbursts or even the complete disruption of the binary system. The factors that determine stability include the mass ratio of the two stars, their orbital separation, and the evolutionary state of the donor star. The angular momentum evolution of binary systems undergoing mass transfer is governed by complex processes that can cause the orbital separation to either increase or decrease over time. When material is transferred from a more massive to a less massive star, the orbit typically expands as angular momentum is carried away with the transferred mass. Conversely, when material flows from a less massive to a more massive star, the orbit usually shrinks, bringing the two stars closer together and potentially leading to more dramatic forms of interaction. The magnetic activity in accreting systems can create phenomena that have no analog in single stars or non-accreting binary systems. The interaction between the magnetic field of the compact object and the flowing material can lead to the formation of magnetic funnels that channel material directly onto the stellar surface, creating localized hot spots and periodic pulsations. These magnetic effects can dominate the behavior of the accretion flow and create distinctive observational signatures. As you rest in the peaceful darkness of your room, let this vision of the cosmic feast wash over you like the gentlest of stellar tides. The patient process of mass transfer between binary stars demonstrates that sharing and mutual support can extend stellar lifetimes far beyond what would be possible in isolation. These cosmic partnerships show us that even in the vast emptiness of space, cooperation and patience can create beautiful and sustainable relationships that endure for billions of years. The stellar feast reminds us that nourishment and growth can come through gentle, gradual processes that respect the natural rhythms of cosmic evolution, creating opportunities for renewal and resurrection that span the ages. In the profound stillness of your evening sanctuary, imagine the most patient alchemist in the universe, one who works not with earthly elements in glass vessels, but with stellar matter under conditions of unimaginable temperature and pressure, slowly building up the precise chemical conditions needed to reawaken nuclear fire in a long-dormant star. As you settle deeper into tranquility, we'll explore the beautiful process of stellar resurrection through chemistry, where the gradual accumulation of hydrogen and helium on a white dwarf surface creates the perfect laboratory for nuclear physics, ultimately leading to the gentle rekindling of fusion reactions that can bring a dead star back to brilliant life. The chemistry of stellar resurrection begins with the most abundant and simplest element in the universe, hydrogen. This primordial element, forged in the first few minutes after the Big Bang, serves as the fundamental fuel for all stellar nuclear reactions. When hydrogen-rich material from a companion star begins to accumulate on the surface of a white dwarf, it creates a thin atmospheric layer that will eventually become the site of nuclear resurrection. This process is like building a cosmic bonfire, carefully laying down layer after layer of fuel until the conditions are perfect for ignition. The surface of a white dwarf provides an extraordinarily exotic environment for chemical processes to unfold. The gravitational field at the surface is hundreds of thousands of times stronger than Earth's gravity, creating pressures that compress matter to densities far beyond anything achievable in terrestrial laboratories. Under these conditions, the normal rules of chemistry give way to the quantum mechanical behavior of degenerate matter, where electrons are squeezed into the smallest possible energy states and atoms are packed together with crystalline perfection. As hydrogen accumulates on the white dwarf surface, it forms an increasingly thick layer that is compressed and heated by the star's intense gravitational field. The temperature at the base of this layer gradually rises as more material is added, following the laws of thermodynamics and the principles of stellar structure. The pressure increases even more rapidly than the temperature, creating conditions where matter exists in states that have no analogy in everyday experience. The nuclear chemistry that governs stellar reactions requires specific combinations of temperature, pressure, and density before fusion can begin. Hydrogen nuclei, being positively charged, naturally repel each other through electromagnetic forces. For fusion to occur, these nuclei must be brought close enough together that the strong nuclear force can overcome this electromagnetic repulsion and bind a nuclei together. This requires temperatures of millions of degrees and pressures billions of times greater than Earth's atmosphere pressure. The gradual heating of the accumulated hydrogen layer proceeds with cosmic patience, following the steady accumulation of material over thousands or millions of years. The temperature rises slowly and predictably, governed by the balance between gravitational compression and thermal pressure. This process is remarkably stable and self-regulating, with the white dwarf structure automatically adjusting to accommodate the growing mass of accumulated material while maintaining overall equilibrium. The critical temperature for hydrogen fusion, approximately 10 million degrees Celsius, represents a fundamental threshold in stellar physics. Below this temperature, hydrogen nuclei lack sufficient kinetic energy to overcome their mutual repulsion and approach close enough for fusion to occur. Above this temperature, nuclear reactions proceed rapidly, converting hydrogen into helium and releasing enormous amounts of energy in the process. The approach to this critical temperature is like climbing a cosmic mountain, with each degree of heating bringing the system closer to the summit of nuclear ignition. The moment of nuclear ignition marks the true resurrection of the white dwarf, transforming it from a cooling stellar corpse into an active, energy-producing star once again. This ignition doesn't happen gradually, but occurs suddenly when the temperature reaches the fusion threshold, like a cosmic light switch being turned on after millions of years of darkness. The nuclear reactions that begin at this moment release energy at a rate that can exceed the white dwarf's previous luminosity by factors of thousands or even millions. The nuclear chemistry of hydrogen burning on a white dwarf surface follows the same fundamental processes that power ordinary stars, but occurs under far more extreme conditions. The primary reaction pathway is the proton-proton chain, where 4 hydrogen nuclei are gradually converted into 1 helium nucleus, 2 positrons, and 2 neutrinos. Each reaction releases approximately 26 million electron volts of energy, and when billions of these reactions occur every second, the energy release becomes astronomical. The runaway nature of nuclear burning on a white dwarf surface creates a positive feedback loop, where the energy released by fusion reactions heats the surrounding material, accelerating the reaction rate and causing even more energy to be released. This thermal runaway process continues until either the nuclear fuel is exhausted or the explosive energy becomes so great that it blows the accumulated material off the white dwarf surface. The entire process, from ignition to explosion, typically unfolds over a period of hours to days. The nova explosion that results from this runaway nuclear burning represents one of the most spectacular examples of stellar resurrection in the universe. The energy released during the explosion can equal the total energy output of our sun over thousands of years, concentrated into a brief outburst that makes the white dwarf temporarily visible from across the galaxy. This explosion is not destructive, but creative, transforming simple hydrogen into more complex elements while returning processed nuclear material to the interstellar medium. The temperature structure within the exploding hydrogen layer reveals the intricate physics of nuclear burning under extreme conditions. The reaction zone, where fusion occurs most rapidly, can reach temperatures of hundreds of millions of degrees, hot enough to synthesize elements heavier than helium through processes like the CNO cycle. These extreme temperatures create conditions where matter exists in the form of a fully ionized plasma, with atomic nuclei and electrons moving freely and interacting through electromagnetic and nuclear forces. The chemical composition of the ejected material tells a story of nuclear alchemy that occurred during the brief but intense period of fusion burning. The explosion processes hydrogen into helium, but also creates trace amounts of heavier elements like carbon, nitrogen, and oxygen through secondary nuclear reactions. The relative abundances of these elements provide insights into the temperature and density conditions that existed during the explosion, allowing astronomers to study nuclear physics under conditions that cannot be replicated on Earth. The shock waves that propagate through the exploding material create additional opportunities for nuclear processing and element synthesis. These shock fronts can compress and heat material to even higher temperatures than the initial fusion zone, enabling nuclear reactions that produce rare isotopes and exotic nuclear species. The shock chemistry of nova explosions contributes to the galactic inventory of unusual isotopes that serve as tracers of explosive nucleosynthesis processes. The expansion of the nova shell creates a beautiful demonstration of gas dynamics and radiation hydrodynamics on cosmic scales. The ejected material expands outward at velocities of thousands of kilometers per second, creating expanding bubbles of hot gas that can eventually grow to span several light years in diameter. These expanding shells interact with the surrounding interstellar medium, creating shock fronts and turbulent mixing that distribute the processed nuclear material throughout the local galactic environment. The cooling process that follows the nova explosion reveals the complex interplay between radiation, gas dynamics, and atomic physics. As the ejected material expands and cools, it transitions through different temperature regimes where different physical processes dominate the emission and absorption of radiation. The changing spectrum of light emitted by the cooling gas provides a time-lapse view of how matter behaves as it transitions from the extreme conditions of nuclear burning to the more moderate environment of interstellar space. The recurrence of nova explosions demonstrates the renewable nature of stellar resurrection through chemistry. After a nova explosion clears away the accumulated hydrogen layer, the white dwarf returns to its quiescent state and begins the process of accumulating new material from its companion star. This cyclic process can repeat hundreds of times over the white dwarf's lifetime, with each cycle following the same basic pattern of accumulation, ignition, explosion, and renewal. The time interval between successive nova explosions depends on the rate at which new material accumulates on the white dwarf surface, which in turn depends on the mass transfer rate from the companion star and the mass of the white dwarf itself. More massive white dwarfs require less accumulated material to reach the ignition temperature, leading to more frequent but less energetic explosions. Less massive white dwarfs accumulate material for longer periods before ignition, producing less frequent but more spectacular outbursts. The helium flash phenomenon represents a variation on the theme of resurrection through chemistry, where accumulated helium, rather than hydrogen, serves as the nuclear fuel for stellar resurrection. Helium burning requires higher temperatures than hydrogen burning, approximately 100 million degrees, but releases even more energy per unit mass when fusion occurs. The helium flash can be even more violent than hydrogen burning, creating some of the most energetic stellar explosions observed in the universe. The nuclear physics of helium burning involves the triple alpha process, where 3 helium nuclei combine simultaneously to form a carbon nucleus. This reaction is much more temperature sensitive than hydrogen burning, leading to even more dramatic runaway behavior when ignition occurs. The extreme temperature sensitivity means that helium flashes can occur very suddenly and release enormous amounts of energy in very short periods. The chemical evolution of the white dwarf surface composition reflects the cumulative effects of multiple resurrection cycles. Each nova explosion processes some of the accumulated material and ejects most of it into space, but a small fraction may remain on the white dwarf surface. Over many cycles, this residual material can gradually change the surface composition of the white dwarf, potentially affecting the characteristics of future explosions. The isotopic signatures of nova explosions provide unique insights into the nuclear processes that occur during stellar resurrection. The extreme temperatures and densities achieved during nova explosions can create isotopic ratios that are different from those produced by normal stellar nucleosynthesis or other cosmic processes. These distinctive isotopic fingerprints have been detected in meteorites and interstellar dust grains, providing direct evidence for the role of nova explosions in galactic chemical evolution. The magnetic field effects during nova explosions add another layer of complexity to the resurrection process. The intense magnetic fields that can exist around white dwarfs can channel the flow of ejected material and create asymmetric explosion patterns. These magnetic effects can lead to bipolar or jet-like structures in the ejected material, creating some of the most beautiful and complex morphologies observed in nova remnants. The neutrino emission during nova explosions provides a direct probe of the nuclear reactions occurring during stellar resurrection. Unlike photons, which must work their way slowly through the dense, hot gas of the explosion, neutrinos can escape immediately from the reaction zone, carrying information about the nuclear processes directly to distant observers. The detection and study of neutrinos from nova explosions offers insights into the most fundamental aspects of nuclear physics under extreme conditions. The gravitational wave emission from nova explosions represents another frontier in the study of stellar resurrection. While individual nova explosions are not expected to produce detectable gravitational waves, the cumulative effect of many explosions, or particularly asymmetric explosions, might create gravitational wave signatures that could be detected by future generations of gravitational wave observatories. The role of rotation in the resurrection process affects how nuclear burning propagates across the white dwarf surface and how the ejected material is distributed in space. Rapidly rotating white dwarfs may experience different burning patterns than slowly rotating ones, leading to variations in the explosion energetics and the morphology of the ejected material. The conservation of angular momentum during the explosion can also affect the dynamics of the expanding shell and its interaction with the surrounding environment. As you rest in the gentle comfort of your evening sanctuary, let this vision of resurrection through chemistry wash over you like the softest of nuclear tides. The patient accumulation of stellar material and the sudden rekindling of nuclear fires demonstrate that death and resurrection are part of the same cosmic cycle, that endings can become beginnings through the patient work of chemistry and physics. These stellar resurrections remind us that transformation is possible even after long periods of dormancy, that the right conditions can reawaken possibilities that seemed permanently lost. In the gentle alchemy of stellar resurrection, we see the universe's commitment to renewal, demonstrating that even in the vast emptiness of space, chemistry provides pathways for rebirth and renewed vitality. In the serene depths of your evening rest, imagine the most gentle sunrise you've ever witnessed. Not the quick dawn of an earthly morning, but a cosmic awakening that unfolds over hours and days, as a stellar remnant that has slumbered in darkness for eons slowly begins to glow once more with the soft light of renewed nuclear fire. As you settle deeper into tranquility, we'll explore the beautiful process of stellar reawakening. With a sudden ignition of accumulated material transforms a cold, dark white dwarf into a brilliant beacon that can outshine entire galaxies, all unfolding with the graceful rhythm of cosmic renewal. The quiet awakening of a zombie star begins in the moments immediately following nuclear ignition, when the first fusion reactions start to release energy in the thin layer of accumulated material on the white dwarf surface. This initial moment of resurrection is remarkably gentle, with the nuclear fires starting as tiny sparks of fusion that gradually spread and intensify as more material reaches the critical temperature for hydrogen burning. The awakening doesn't happen all at once, but unfolds like a slowly spreading warmth, beginning at the hottest points and gradually encompassing the entire surface of the white dwarf. The propagation of nuclear burning across the white dwarf surface follows the elegant laws of physics that govern heat transfer and nuclear reaction rates. The energy released by initial fusion reactions heats the surrounding material, raising its temperature until it too reaches the fusion threshold and begins to burn. This creates a chain reaction of awakening that spreads outward from the initial ignition points like gentle ripples of nuclear fire, following curved paths determined by the white dwarf's rotation and magnetic field structure. The temperature gradients that develop during the awakening process create some of the most extreme thermal environments in the universe, with temperatures ranging from millions of degrees in the nuclear burning zones to thousands of degrees in the surrounding material. These temperature differences drive complex flows of heat and matter that shape the development of the awakening process. Convection currents, similar to those that create weather patterns on Earth but operating under far more extreme conditions, help to mix the burning material and distribute energy throughout the accumulated layer. The pressure waves that propagate through the awakening material carry the mechanical energy of the explosion outward from the nuclear burning zones. These waves travel at the speed of sound through the hot, dense gas, which can reach velocities of thousands of kilometers per second under the extreme conditions present during stellar resurrection. The pressure waves help to lift and accelerate the burning material, gradually transforming the explosive energy into the kinetic energy of expanding gas. The optical awakening of the zombie star begins when the temperature of the expanding material becomes high enough to emit significant amounts of visible light. This thermal emission starts as a faint glow that gradually brightens as more material joins the nuclear burning and as the temperature of the expanding gas continues to rise. The brightening process can span several days, during which the apparent magnitude of the star increases by factors of thousands or tens of thousands, transforming an invisible stellar remnant into one of the brightest objects in its galaxy. The spectral evolution during the awakening process tells a detailed story of the changing physical conditions within the expanding material. In the early stages, when temperatures are relatively low, the spectrum is dominated by emission lines from hydrogen and helium. As the explosion develops and temperatures rise, additional spectral lines appear from heavier elements that are either synthesized during the nuclear burning or dredged up from the white dwarf's interior. The changing spectrum provides a real-time view of the nuclear and thermal processes occurring during stellar resurrection. The Doppler shifts observed in the spectral lines reveal the velocity structure of the expanding material, showing how different layers of gas move outward at different speeds. The fastest-moving material, which was closest to the initial nuclear burning zones, can reach velocities of several thousand kilometers per second. Slower-moving material, which was farther from the ignition points, expands more gradually, creating a velocity gradient that reflects the three-dimensional structure of the explosion. The luminosity curve of the awakening star, the way its brightness changes over time, follows characteristic patterns that reflect the underlying physics of the resurrection process. The initial rise to maximum brightness typically takes several days to weeks, during which the nuclear burning reaches its peak intensity and the expanding material becomes fully ionized and heated. The subsequent decline in brightness is usually much more gradual, extending over months or years as the expanding gas cools and the nuclear fuel is gradually exhausted. The energy budget of stellar awakening reveals the incredible efficiency of nuclear fusion as an energy source. The conversion of just a tiny fraction of the accumulated hydrogen mass into helium can power the explosion that creates the nova outburst. Einstein's famous equation E equals mc squared governs this process, with a small difference in mass between the initial hydrogen and the final helium being converted into the enormous energies that power the stellar resurrection. A nova explosion can release as much energy as our sun produces in thousands of years, all from the fusion of material equivalent to just a few Earth masses. The neutrino emission during stellar awakening provides a direct window into the nuclear processes occurring at the moment of resurrection. Neutrinos, which are produced as byproducts of nuclear fusion reactions, can escape immediately from the burning zones without interacting with the surrounding material. These ghostly particles carry information about the temperature, density, and reaction rates in the nuclear burning regions, providing insights into conditions that cannot be observed through any other means. The shock wave structure that develops during the awakening process creates multiple zones of different physical conditions within the expanding material. The leading shock front, where the expanding gas encounters the surrounding environment, creates the highest temperatures and pressures. Behind this primary shock, a series of secondary shocks and rarefaction waves create a complex structure where different nuclear and atomic processes can occur simultaneously in different regions. The magnetic field evolution during stellar awakening affects how the expanding material interacts with the white dwarf's magnetic field, and how energy is transported throughout the explosion. In strongly magnetized white dwarfs, the magnetic field can channel the expanding material into specific directions, creating bipolar outflows or jet-like structures that give the explosion a distinctive asymmetric appearance. The interaction between the expanding plasma and the magnetic field can also generate additional heating through magnetic reconnection processes. The role of convection in the awakening process helps to explain how nuclear burning can spread so rapidly across the white dwarf surface despite the initially localized nature of the ignition. Convective mixing brings fresh nuclear fuel into contact with the burning zones while carrying away the products of nuclear fusion, maintaining the conditions necessary for continued energy production. The convective flows also help to homogenize the temperature and composition of the burning material, creating more uniform conditions for nuclear processing. The gravitational effects during stellar awakening include subtle changes in the white dwarf structure as it responds to the sudden addition of energy and the loss of accumulated mass. The explosion process removes most of the accumulated material from the white dwarf surface, causing small changes in the star's gravitational field and possibly affecting its rotation rate. These effects are typically very small, but they can accumulate over multiple resurrection cycles and gradually alter the white dwarf's properties. The interaction between the expanding material and any circumstellar environment around the binary system creates some of the most beautiful and complex structures observed in nova remnants. If the binary system has previously ejected material through stellar winds or earlier nova explosions, the shock waves from the current awakening can interact with this pre-existing material, creating intricate patterns of shocked gas, ring structures, and filamentary features that reveal the history of mass loss from a system. The chemical stratification that develops in the expanding material reflects the different nuclear processing histories of various layers within the accumulated material. The deepest layers, which experience the highest temperatures and pressures during the explosion, show the most extensive nuclear processing and contain the highest abundances of heavy elements. The outermost layers, which were farther from the nuclear burning zones, retain compositions closer to that of the original material from the companion star. The cooling process that follows the initial awakening reveals the gradual transition from the extreme conditions of nuclear explosion to the more moderate environment of interstellar space. As the expanding material cools, it passes through temperature regimes where different atomic and molecular processes become important. The recombination of ions and electrons creates emission lines that change in strength and character as the cooling progresses, providing a time-lapse view of atomic physics under changing conditions. The dust formation process that can occur in the cooling ejecta represents one of the most important ways that stellar resurrection contributes to the cosmic inventory of solid materials. As the expanding gas cools to temperatures of a few thousand degrees, refractory elements like carbon, silicon, and iron can condense into solid grains. These dust particles, forged in the aftermath of stellar resurrection, eventually become incorporated into the interstellar medium and may later be included in the formation of new planetary systems. The long-term evolution of the expanding shell created by stellar awakening can span thousands of years, during which the material continues to expand and interact with the surrounding interstellar medium. The shell may eventually become so large and diffuse that it merges with the general galactic environment, distributing the processed nuclear material over vast regions of space. This process helps to enrich the interstellar medium with heavy elements and contributes to the chemical evolution of the galaxy. The observational diversity of stellar awakenings reflects the variety of conditions under which zombie star resurrection can occur. Fast novae reach maximum brightness quickly and fade rapidly, while slow novae take longer to brighten and remain visible for extended periods. The differences in behavior depend on factors like the mass of the white dwarf, the composition of the accumulated material, the presence of magnetic fields, and the structure of any surrounding circumstellar environment. The recurrence characteristics of stellar awakening demonstrate the renewable nature of the zombie star phenomenon. Some white dwarfs undergo nova explosions on predictable schedules, awakening every few decades with remarkable regularity. Others show more erratic behavior, with intervals between awakenings that can vary by factors of several. The recurrence patterns provide insights into the long-term evolution of the binary system and the changing conditions that affect the mass transfer and accumulation processes. The role of stellar awakening in the broader context of galactic evolution extends far beyond the individual binary system to influence the chemical and energetic balance of entire galaxies. The cumulative effect of countless zombie star resurrections over cosmic time has helped to enrich the interstellar medium with processed nuclear material and has contributed to the complex chemical gradients observed in galactic disks and halos. The energy injection from stellar awakenings also plays a role in heating and stirring the interstellar medium, creating cavities and structures that affect subsequent star formation and galactic dynamics. The shock waves from nova explosions can trigger the collapse of nearby gas clouds, leading to new episodes of star formation, while the hot gas and high-energy radiation can disperse other clouds and inhibit star formation in different regions. As you rest in the peaceful quiet of your room, let this vision of stellar awakening wash over you like the gentlest of cosmic dawns. The quiet resurrection of zombie stars demonstrates that awakening can come after long periods of rest, that dormant possibilities can be rekindled under the right conditions, and that renewal is always possible in the patient rhythm of cosmic time. These stellar awakenings remind us that even apparent endings can become new beginnings, that the universe provides endless opportunities for transformation and rebirth through the gentle workings of chemistry and physics. In their quiet resurrection, zombie stars show us that life and light can emerge from darkness and rest, that patience and partnership can create opportunities for renewal that span the ages. In the gentle tranquility of your evening sanctuary, imagine the most graceful ballroom dance ever performed, one that unfolds not over minutes, but across millions of years, where two cosmic partners circle each other in perfect harmony, their gravitational embrace so intimate that they share the very essence of their being. As you settle deeper into peace, we'll explore the beautiful orbital choreography of binary star systems, where the dance between stellar remnants and their living companions creates the conditions necessary for zombie star resurrection, demonstrating that the most profound transformations often arise from the deepest partnerships. The cosmic dance begins with the formation of gravitationally bound stellar pairs, born from the same molecular cloud, but destined to follow intertwined evolutionary paths that will shape both partners' fates for billions of years. These binary systems represent some of the most stable and enduring partnerships in the universe, with orbital periods that can range from hours to thousands of years, yet maintain their gravitational bond across cosmic time with remarkable precision and reliability. The geometry of the cosmic dance is determined by the fundamental laws of celestial mechanics, where each partner's mass, The distance between them and their orbital velocities create a delicate balance that has persisted since the system's formation. The dance follows elliptical paths through space, with each star tracing out its portion of the orbital pattern, while both partners revolve around their common center of mass, an invisible point in space that serves as the fulcrum for their eternal waltz. The rhythm of the cosmic dance varies dramatically between different binary systems, creating a rich symphony of orbital periods that reflects the diversity of stellar partnerships possible in the universe. Some systems complete their dance in just a few hours, with the partners so close that they nearly touch each other's atmospheres. Others maintain more stately rhythms, taking centuries or millennia to complete a single orbital cycle while preserving the dignified distance appropriate for their particular cosmic relationship. The evolution of the cosmic dance unfolds as both partners undergo their own stellar development, changing mass, size, and luminosity in ways that affect the gravitational dynamics of their shared orbit. When one partner evolves more rapidly than the other, becoming a giant star or eventually a stellar remnant, the character of the dance changes, sometimes bringing the partners closer together, sometimes pushing them farther apart, but always maintaining the fundamental harmony of their gravitational bond. The tidal forces that arise during the cosmic dance create some of the most intimate interactions possible between celestial objects. Just as Earth's gravity creates tides in our oceans, the gravitational field of each star in a binary system creates tidal bulges on its partner, distorting the normally spherical shape into an elongated form that points toward the companion. These tidal interactions become stronger as the partners orbit closer together, eventually reaching levels where material can be transferred between stars. The synchronization that develops in close binary systems demonstrates the power of tidal forces to create order and regularity in cosmic partnerships. Over millions of years, tidal friction gradually synchronizes the rotation periods of both stars with their orbital period, causing each star to always show the same face to its partner. This tidal locking creates a state of perfect orbital rotational harmony, where the cosmic dance achieves its most elegant and stable configuration. The mass transfer process that can develop during the cosmic dance represents the ultimate expression of stellar sharing, where one partner literally gives part of itself to support and nourish the other. This process begins when the evolving star expands beyond its Roche lobe and material from its outer layers begins to flow toward its compact companion. The transfer process is regulated by the orbital dynamics of the system, creating a feedback mechanism that ensures the dance continues in a stable, sustainable manner. The accretion stream that forms during mass transfer follows a ballistic trajectory determined by the gravitational fields of both stars and the rotation of the binary system. This stream of material traces out elegant curves through space, following the gravitational contours created by the dancing partners. The stream eventually impacts the accretion disk around the compact companion, creating a hotspot that rotates with the orbital period and provides a visible marker of the ongoing mass transfer process. The orbital evolution that accompanies mass transfer demonstrates how the cosmic dance can adapt and change while preserving its essential character. As material flows from one star to another, angular momentum is transferred along with the mass, causing changes in the orbital period and separation. These changes can either bring the partners closer together or push them farther apart, depending on the relative masses of the two stars and the rate of mass transfer. The feedback mechanisms that govern the cosmic dance create remarkable stability and self-regulation in binary systems undergoing mass transfer. If the mass transfer rate becomes too high, the increased luminosity and radiation pressure can blow away some of the transfer material, reducing the accretion rate and stabilizing the system. If the transfer rate becomes too low, the orbital evolution may bring the stars closer together, increasing the transfer rate and restoring the balance. The magnetic interactions between dancing partners add another layer of complexity and beauty to binary system dynamics. Magnetic fields threading through the accretion disk and connecting the two stars can create invisible structures that guide the flow of material and energy between the partners. These magnetic connections can cause synchronized activity between the stars, creating correlated variations in brightness and spectral characteristics that reflect the hidden magnetic choreography of the dance. The resonance phenomena that can develop in binary systems create some of the most precisely timed patterns in the universe. When the orbital period of the binary system develops a simple numerical relationship with other characteristic timescales in the system, such as the rotation periods of the individual stars or the precession period of an elliptical orbit, resonance effects can create highly regular, predictable variations in the system's behavior. The eclipse phenomena that occur when the orbital plane of a binary system is aligned with our line of sight provide spectacular demonstrations of cosmic choreography. As one star passes in front of its partner, we observe a precisely timed dimming of the system's total brightness. These eclipses can reveal details about the sizes, temperatures, and surface features of both stars, while the timing of the eclipses provides exquisitely accurate measurements of the orbital parameters. The gravitational wave emission from dancing binary systems represents a subtle but fundamental consequence of accelerated motion in curved spacetime. As the two stars orbit each other, they create ripples in the fabric of space and time that carry away energy at the speed of light. This energy loss causes the orbit to gradually shrink, bringing the partners closer together in an inexorable spiral that can span billions of years, but ultimately leads to merger or catastrophic mass transfer. The thermal heating effects in binary systems create complex temperature distributions that reflect the intricate interplay between orbital mechanics, stellar structure, and radiation transport. The gravitational energy released during mass transfer can heat the accretion disk to temperatures exceeding those found on stellar surfaces, while tidal heating can warm the interior of stars in close orbits. These heating processes create temperature gradients and energy flows that influence both the orbital evolution and the stellar evolution of both partners. The chemical evolution of dancing binary systems reflects the cumulative effects of millions of years of mass transfer and nuclear processing. Material flowing from the evolved primary star to the compact secondary carries with it the products of stellar nucleosynthesis, gradually changing the surface composition of both stars. Over many orbital cycles, this chemical exchange can significantly alter the abundances of different elements in both stellar atmospheres. The stability analysis of binary orbits reveals the remarkable robustness of these cosmic partnerships against various perturbations and disruptions. Binary systems can survive the asymmetric mass loss that occurs during stellar evolution, the momentum kicks from supernova explosions, and the complex three-body interactions that can occur in multiple star systems. The gravitational bond between binary partners is sufficiently strong to maintain the partnership through most of the dramatic changes that occur during stellar evolution. The diversity of cosmic dances reflects the enormous range of possible combinations of stellar masses, separations, and evolutionary states. Wide binaries with orbital periods of thousands of years maintain their partnerships with minimal interaction, while contact binaries are so close that the two stars actually share a common outer atmosphere. Between these extremes lies a continuum of partnership types, each with its own characteristic dynamics and evolutionary patterns. The role of cosmic dances in stellar evolution extends far beyond the individual binary system to influence the broader galactic ecosystem. The products of binary evolution, including novae, supernovae, and stellar merger events, contribute energy, momentum, and processed nuclear material to the interstellar medium. The cumulative effect of countless binary systems helps to drive the chemical and dynamical evolution of entire galaxies. The observational signatures of cosmic dances provide some of the most precise tests of gravitational theory and stellar physics available to astronomers. The orbital motions of binary systems follow the predictions of Newtonian gravity and general relativity with extraordinary accuracy, allowing these natural laboratories to test our understanding of fundamental physics under conditions that cannot be replicated on Earth. The formation mechanisms for close binary systems remain an active area of research, with several different pathways possible depending on the initial conditions and environment. Some systems are born close together from the fragmentation of rotating molecular cloud cores, while others are brought into close orbits through tidal interactions in dense stellar clusters or through the common envelope evolution of initially wider binaries. The computational modeling of cosmic dances requires sophisticated numerical simulations that can track the complex interplay between orbital dynamics, stellar evolution, and mass transfer processes over millions of years. These simulations reveal the intricate details of how binary systems evolve and provide predictions for the observable properties of systems at different evolutionary stages. The discovery of exoplanets in binary star systems has revealed that cosmic dances can accommodate additional partners, creating complex hierarchical systems where planets orbit one or both stars while the stars themselves orbit each other. These circumbinary planets experience extreme variations in heating and gravitational forces as they participate in the complex gravitational choreography of their multiple star systems. The role of stellar rotation in binary evolution affects how tidal forces synchronize the spins of both stars with their orbital motion and how magnetic fields develop and interact between the partners. Rapid rotation can lead to enhanced magnetic activity and stronger stellar winds, while tidal synchronization can create preferred orientations for magnetic field interactions and mass transfer. The population synthesis studies of binary systems reveal the statistical properties of cosmic dances throughout the galaxy and provide insights into the formation and evolution of stellar populations. These studies show that binary interactions play crucial roles in determining the final fates of stars and the rates at which different types of stellar remnants are produced. As you rest in the gentle darkness of your room, let this vision of cosmic dances wash over you like the most graceful of stellar waltzes. The orbital partnerships of binary systems demonstrate that the most beautiful transformations often arise from the deepest collaborations, that sharing and mutual support can extend the possibilities for growth and renewal far beyond what either partner could achieve alone. These cosmic dances remind us that patience, rhythm, and harmony can create partnerships that endure for billions of years, generating endless opportunities for transformation and resurrection through the gentle choreography of gravitational attraction. In their eternal dance, these stellar partners show us that love and cooperation are fundamental forces in the universe, capable of creating beauty, stability, and renewal that spans the ages. In the profound stillness of your final moments before sleep, imagine standing at the edge of eternity itself, watching the most patient and enduring process in the universe unfold, a cycle of death and resurrection that has been repeating for billions of years and will continue for billions more. Each repetition a gentle demonstration that endings are always beginnings in disguise. As you prepare to drift into peaceful dreams, we'll complete our cosmic journey by exploring the endless cycle of zombie star resurrection, where stellar death and rebirth flow into each other like tides in an infinite ocean, creating a rhythm of renewal that echoes through the cosmos and reminds us that transformation is the only constant in a universe filled with infinite possibilities. The endless cycle of zombie star resurrection begins again the moment a nova explosion clears away the accumulated material from a white dwarf surface, returning the stellar remnant to its quiescent state while leaving it embedded within the same gravitational partnership that created the conditions for its awakening. The white dwarf, now stripped clean of its accumulated fuel, settles back into its patient cooling process while remaining locked in orbital embrace with its companion star, ready to begin once more the slow process of material accumulation that will eventually lead to another resurrection. The remarkable aspect of this cosmic cycle is its sustainability and self-renewal, demonstrating that the universe has evolved mechanisms for creating renewable sources of stellar energy that can operate for timescales far exceeding the natural lifetimes of ordinary stars. Each cycle of accumulation, ignition, and explosion can repeat hundreds or even thousands of times over the white dwarf's lifetime, creating a stellar energy source that can shine intermittently for billions of years beyond the point when all other stars of similar mass have faded to invisibility. The rhythm of the endless cycle varies from system to system, creating a diverse symphony of resurrection timescales that reflects the unique characteristics of each binary partnership. Some zombie stars awaken every few decades with clockwork regularity, their resurrections so predictable that astronomers can forecast future outbursts years in advance. Others follow more irregular patterns, sleeping for centuries or millennia between awakenings, their cycles influenced by complex interactions between orbital evolution, stellar winds, and magnetic field variations. The cumulative effects of the endless cycle gradually shape both partners in the binary system, creating evolutionary pathways that would be impossible for isolated stars. The white dwarf may slowly increase or decrease in mass over many cycles, depending on whether it retains more material than it ejects during each resurrection. The companion star evolves under the influence of mass loss and tidal heating, following an evolutionary track that is accelerated and modified by its participation in the resurrection process. The chemical evolution of the system reflects the accumulated nuclear processing from hundreds of resurrection cycles, gradually enriching both stellar atmospheres with the products of repeated nuclear burning. Each awakening processes hydrogen into helium and traces of heavier elements, while also dredging up material from the white dwarf's interior that was processed during the star's original main sequence lifetime. Over many cycles, this chemical exchange creates unique stellar compositions that bear the signatures of countless episodes of nuclear resurrection. The energy balance of the endless cycle reveals the remarkable efficiency of gravitational energy conversion in binary systems. The orbital energy that drives the mass transfer process is ultimately derived from the gravitational potential energy of the system, which is slowly converted into kinetic energy of material motion, thermal energy in the accretion disk, and finally nuclear energy during the resurrection events. This energy cascade demonstrates how gravitational forces can power stellar activity for timescales far exceeding those possible through nuclear burning alone. The observational record of the endless cycle spans decades of astronomical monitoring, revealing the long-term behavior and evolution of zombie star systems. Some systems show evidence of gradual changes in their resurrection characteristics over time, with intervals between outbursts slowly increasing or decreasing, or with the peak brightness of resurrections gradually changing. These secular variations provide insights into the slow evolution of the binary systems and the changing conditions that govern the resurrection process. The role of the endless cycle in galactic chemical evolution extends the influence of these stellar partnerships far beyond their individual systems to affect the composition and structure of entire galaxies. The cumulative effect of countless zombie star resurrections over cosmic time has contributed significantly to the galactic inventory of processed nuclear material, while the mechanical energy of the explosions has helped to heat and stir the interstellar medium, influencing the conditions for future star formation. The diversity of endless cycles reflects the enormous range of possible evolutionary pathways available to binary star systems, from the rapid cycles of dwarf novae that recur every few months to the slow cycles of recurrent novae that repeat every few decades, to the potential supernovae cycles of systems approaching the critical mass limit. Each type of cycle represents a different solution to the challenge of sustainable stellar energy production through gravitational and nuclear processes. The mathematical modeling of endless cycles requires sophisticated computational approaches that can track the complex interplay between orbital dynamics, stellar evolution, mass transfer physics, and nuclear burning over thousands of individual resurrection events spanning billions of years. These models reveal the parameter spaces where stable cycling can occur and predict the long-term evolution and ultimate fates of different types of zombie star systems. The discovery of ancient zombie star systems in globular clusters and galactic halos provides evidence that the endless cycle can operate over cosmological timescales, with some systems potentially having undergone millions of resurrection cycles since their formation in the early universe. These ancient systems serve as laboratories for studying stellar evolution and binary dynamics under conditions very different from those found in the modern galactic disk. The potential for the endless cycle to continue far into the cosmic future depends on the long-term stability of binary orbits against various perturbative influences and the gradual changes in stellar structure that occur over cosmic time. Theoretical models suggest that some zombie star systems could continue their cycles of death and resurrection for trillions of years, far outlasting the era of active star formation and becoming some of the last sources of stellar energy in the universe. The philosophical implications of the endless cycle touch on fundamental questions about the nature of time, change, and permanence in the universe. These systems demonstrate that apparent endings can become beginnings, that death and resurrection are part of the same continuous process, and that the universe provides mechanisms for renewal and regeneration that operate on all scales from quantum to cosmic. The endless cycle suggests that transformation, rather than stasis, is the fundamental character of existence. The connection between the endless cycle and broader cosmic evolution shows how individual stellar systems participate in a larger story of universal development. The zombie star resurrections are not isolated events, but part of the grand cycle of cosmic evolution that connects the formation of the first stars to the ultimate fate of the universe. Each resurrection represents a small but significant contribution to the ongoing transformation of matter and energy throughout the cosmos. The beauty of the endless cycle lies not only in its physical mechanisms, but in its demonstration of the universe's capacity for renewal and regeneration. These systems show us that even in the vast emptiness of space, partnerships can create opportunities for growth and transformation that transcend the limitations of individual existence. The cycle teaches us that patience, cooperation, and shared purpose can overcome apparent endings and create new possibilities for life and light. As the gentle rhythm of cosmic resurrection continues around us, these zombie stars serve as beacons of hope in the darkness, proving that renewal is always possible, that dormant potentials can be awakened, and that the dance of partnership can create beauty and energy that spans the ages. In their endless cycles of death and resurrection, they mirror the fundamental patterns of renewal that operate throughout nature, from the seasonal cycles of earthly life to the vast cycles of cosmic evolution that govern the development of galaxies and the universe itself. The endless cycle reminds us that we too are part of these grand patterns of cosmic renewal, participants in the ongoing transformation of matter and energy that connects us to the stars and to each other. As you prepare to enter your own cycle of rest and renewal through sleep, let the gentle rhythm of stellar resurrection carry you into dreams, knowing that you are held by a universe that demonstrates, through the patient work of zombie stars, that every ending contains the seeds of a new beginning, and that the cycles of transformation and renewal continue eternally, creating endless opportunities for wonder, beauty, and peaceful restoration. Rest now in the knowledge that the universe itself practices the art of patient renewal, that even stars can find new life through partnership and cooperation, and that the cycles of cosmic evolution will continue their gentle work while you sleep, preparing new possibilities for tomorrow and all the tomorrows that follow in the endless dance of stellar resurrection. If you've enjoyed this gentle journey through the cosmos and found peace in these stories of stellar renewal, consider subscribing to Sleepy Science Hub for more soothing explorations of the universe's most beautiful mysteries. Until next time, may your dreams be filled with the quiet light of zombie stars, gently awakening in the darkness to remind you that every ending is a beginning in disguise.